Okay, next problem, 21. Part A, let's find the vertical asymptotes. So we know that these occur at zeros in the denominator. So if I rewrite this as 5 over x times x minus 5, I know those are going to be x equals 0 and x equals 5 written as equations of lines. Now, none of these are wholes because wholes are factors that cancel. So it looks like this one has two vertical asymptotes. You could graph it to double check, but it will have these two asymptotes that are vertical. Horizontal asymptotes then, the exponent's higher in the bottom, the degree's higher in the bottom than it is the top. That means the line y equals 0 is the horizontal asymptote. And once again, those rules are on your formula sheet under chapter 2 right here. That's everything you'll need to know for that. Okay, the next one, same thing for the vertical asymptotes. These occur at zeros in the denominator, and it looks like x equals 4 is the 0 in the denominator, so that'd be the vertical asymptote. And no factors cancel, so there's no hole. Horizontal asymptotes then, looks like we have the same exponent, same degree, therefore we do the ratio of the leading coefficients, which is 3 over 1, which should be y equals 3. And the last one's a little bit trickier. The vertical asymptotes are zeros at the bottom, so we have to take this x squared plus 10 and figure out what the zeros are. Set equal to 0, square both sides, and then you can subtract 10 from both sides and take the square root. Now, this thing doesn't have any real zeros then. We kind of know that because this x squared plus 10, we know right here, this function is a parabola that's been shifted up 10 units. We know that doesn't have any real zeros. So there's no x's that I can stick in to get a 0 in the bottom, therefore there are no vertical asymptotes. Horizontal asymptotes. Typically, the horizontal asymptotes would be ratios of leading coefficients when the exponent's the same in the top and the bottom. Because this square root, we actually end up with plus or minus. The square root of x squared is x to the first, which would be the same exponent. So the ratio of the leading coefficients would be 7 to 1. But we also have y equals negative 7 here. And if you're not sure about that, that's not something we've really done all year. You can look at the graph as well. And you can kind of notice that, hey, that's the first degree if I take the square root of x squared. Therefore, I'll do the ratio of leading coefficients. That gives me 7. And then you can also see negative 7 as well. And you can check this if you do 7 and negative 7 and take a look at that graph. You'll see that those are horizontal asymptotes. Okay, the next problem says graph the function and state the intervals on which the function is increasing. So the first one, if we graph it, we get a cubic function here. Obviously, this function is increasing always. It's never decreasing here. Cubics can decrease if there's a middle part that goes like this, but in this case, there's not. You can, and if you want to make sure, you can always zoom in. If we zoom in, hit 2, hit enter in the middle, we can take a better look at this and actually see if we do have any areas where it's increasing or decreasing. You can repeat that if you'd like, and the function doesn't have any behavior of increasing or decreasing here. Now, once again, that actually comes from these other terms anyway, that increasing and decreasing part. So we know that this one's going to always be increasing. So our answer would be negative infinity to infinity if we're going to talk about intervals. Okay, the next problem gives a rational function here. If we look at the graph, we can see that it's got two vertical asymptotes. We know they're at 1 and negative 1 because that's the zeros of our denominator. So there's our vertical asymptotes. And we know it's then, if we're talking about increasing, it's increasing from negative infinity all the way up to negative 1, as well as, and technically I can include this endpoint. I wouldn't be super picky about that. And then from negative 1 to positive 1, as well as from positive 1 to positive infinity. That's actually the domain of the function. This function is always increasing. As x gets bigger, so is y. So the domain of the function is exactly the same answer to the question of when is this function increasing. Okay, the next problem wants us to do the composition f of g of x. So we're going to take g right here, and we're going to plug it right in for that x. So that's going to give us the square root of x squared minus 4. I can't simplify that at all. That's a difference of 2 squares, so I could rewrite it, but I can't simplify it. So the next thing we need to do is give its domain. The domain of this, you would think, would be x squared minus 4. It has to be bigger than or equal to 0, obviously, because we can't have negatives underneath this radical. So if we solve this, we get x squared is greater than or equal to 4. If we add 4 to both sides, square root both sides, we get x is greater than or equal to 2. We also get x is less than or equal to negative 2 if we do switch the sense and do the plus or minus. So there's the domain. So we would use the word or here. If you're not sure, I like to use a number line to visualize it. It wants all the numbers that are bigger than 2, which would be that closed circle all the way that way forever, and then all the numbers less than negative 2, which would be that circle all the way to the left forever. So in interval notation, that would be negative infinity all the way to negative 2, including negative 2, as well as positive 2 all the way up to positive infinity. So there's the interval notation that we would use for the domain, and that's our answer. Now, we do want to look at restrictions from the original function g, because we need to take the most restricted domain. And in this case, there are no restrictions from g, because that's a quadratic that is defined for all real numbers for its domain. So my answer is right here. Next question gives us a 4th degree polynomial. We know what this looks like. It looks something like that. If the leading coefficient is positive, which it is, and we have an even degree, it's basically a basic U shape. So when they talk about limits, the limit as x goes to positive infinity of this function would be positive infinity, as you can tell. And then also the limit as x approaches negative infinity of this function would be positive infinity as well. Next problem just wants us to match the polynomial function with its graph. Obviously we could graph this in our calculator. We will have our calculator on the exam. And you'll notice it's a cubic, so we can rule out the even shaped function, so it's got to be between these two. And I can see that this has been shifted up 55 units, so I can tell that it's going to be A. And like I said, grab it within this window, and you'll get this exact same graph. Okay, next one, 39, wants us to sketch a graph and state the degree, list the zeros. This is degree 4. Because I've got it's degree 3. I've got one exponent here and one here, so when I FOIL it all out, I'd have x cubed. The zeros, x equals 0, that's got a multiplicity of 1. And then I also have x equals 3, that has a multiplicity of 2. So when I go to graph this, it's a degree 3, I know the zeros are at 0 and 3. Even multiplicities means the function hits and turns around, while odd multiplicities mean the function changes signs. So what this must look like is a basic odd function, cubic function, where it touches this even multiplicity at 3 and turns back around. So there's a rough sketch of 39, and you can check this in your calculator as well. The next one, if we were to FOIL all this out, we'd end up with a degree 5. So we know it's got the same basic shape of that odd pattern. We know the zeros are at 1 and also negative 2. And we know that that 0 that's at 1 is an odd multiplicity of 3. And the 0 that's at negative 2 is an even multiplicity of 2. So what that means is the function touches this 0 and changes signs there. I'm sorry, it's an even, so it means it touches and turns around. And then at 1, that's an odd multiplicity, so the function changes signs there. So it should look something like that. All right, the next problem says match the polynomial function with the given zeros and multiplicities. We know that would be B. The reason why is because we have two zeros, one at negative 3 and one at 2. The one at negative 3 is an even multiplicity, so the function turns around. And then at the other 0, at 2, it's got an odd multiplicity, so the function changes y value there. So it would look like this. The next problem wants us to find out the zeros of this 4th degree quartic function. We can graph this in our calculator, and what we can see is it's got two rational zeros at negative 1 and 1. Now we could use the rational zeros theorem as well if we didn't have a calculator, and we would have taken ratios of the leading coefficient divided by the last, and we could find as you plug these in, 1 and negative 1 would give you the zeros. That means that two of our factors are x minus 1, x plus 1. And it means that then there's a quadratic left over. Now it could be two linear factors or it could be an irreducible quadratic. Either way, they want us to write the linear factorization, so we're going to have to write this all out. What I like, you could do long division. If you take this quadratic right here, if you FOIL it out and divide it into this polynomial, you'll get what's left over. I like to do synthetic division though, so we're going to take -1 and 1, and we're going to divide it in to this polynomial, 1, 1, 5, -1, and -6. Drop down the 1 and multiply. If you add, and then multiply, and then add, and then multiply, and then add, and then multiply, you should get no remainder, which is a good sign. So what that means is that this quadratic that's left over is x squared plus 0x, I'm sorry, this cubic right here that's left over is x cubed plus 0x squared plus 5x minus 6. Now I can divide this factor into it. So I can divide 1 into it. And actually, I'm dividing this factor now, but I'll divide 1 into this in this polynomial, 1, 0, 5, -6. Drop down the 1, multiply, add, multiply, add, multiply, and you get no remainder. So what that means is this quadratic right here is x squared plus x plus 6. So there's my factorization. Now, technically they wanted us to do a linear factorization, and this is what's called an irreducible quadratic. I know it's irreducible because it won't factor. It's shifted up, so it's got no real zeros. There's only imaginary zeros or complex zeros that comes from this quadratic. To find those, I guess I can just use the quadratic formula real quick. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. This would be -23 inside of here over 2. And so technically, if I am going to write the linear factorization, I would need to write this as 2 linear factors, and it would be x minus one of these, which would be 1 plus the square root of, I'll write it as I square root of 23 all over 2. And then I would also have x minus the other one, which is 1 minus I square root of 23 all over 2. So there's my, this plus these other 2 linear factors there would give us the complete linear factorization. Okay, the next problem wants to find the horizontal and vertical asymptotes again, but this time use limits to describe the behavior around those asymptotes. So let's factor everything, and this turns into x times x minus 1. Now we can see the vertical asymptotes. Those occur at zeros in the denominator that don't cancel. So in this case we have x equals 0, and we also have x equals 1. The horizontal asymptotes, in this case, we have a higher degree in the bottom than the top, so that'd be the line y equals 0. Now if we want to describe the behavior of the around these asymptotes, the best thing to do is to graph it, and then take a look. So now we can say the limit as x approaches the vertical asymptote 0, as x approaches 0 from the left of this function, is positive infinity. We could say the limit as x approaches 0 from the right, coming from the other direction now, you see it goes down to negative infinity. You could say the limit as x approaches 1 then, let's go from the left here, you go down to negative infinity. And then if you approach 1 from the right of this function, you'll notice that you go up to positive infinity. And then we can also have the limit as x goes to infinity, the end behavior as well. And you can see that that goes to 0. We can do the other way as well as we go to negative infinity. This function also goes to 0 until all the way to the left as well. Alright, one more. We've got vertical asymptotes at zeros at the bottom. If we factor this thing, 1 and -1, because the bottom is the difference of 2 squares, it factors like this. And then we have the ratio of leading coefficients, because we have the same degree in the top and bottom, gives us y equals 2. If we look at the graph, I'm running out of time in this video, so I'm just going to write them all down. Here's, if you go to negative infinity, you go to 2. If you go to positive infinity down here, you go to 2 as well. And then we've got the behavior around the asymptotes, which would be all right here in the middle.